I'm delighted to be here as a moderator and to introduce speakers. I imagine you've already seen at the Symposium web for speakers, so I can call 5 speakers' names at this opening. Ms. Colleen Peters, Mr. Ken Childress, Ms. Karen Cove, Mr. Andrew Talbot, and Mr. Charles de Jongh. Here, I can provide you with some guidance on this session. Firstly, this session will be recorded, and we are open to questions at the Q&A box below. Please post your questions there. So, let's start the session. The first speaker is Ms. Colleen Peters. She is bathymetry data manager of Saildrone. Colleen has a breadth of experience acquiring and managing data collected with a wide variety of scientific instrumentation. Colleen, floor is yours.
Excellent, thank you so much. Thank you everyone for having me. Excited to be here, and today I'm going to talk to you a little bit about what it's been like to map the deep sea under sail with a brand new sailing platform. So just to note, my maritime career actually began on sailing vessels. So I was working on traditional sailing vessels, teaching people how to sail, how to take care of the ship, navigate, all of that good stuff. And then I moved on to oceanographic research vessels, which is where I learned how to map the seafloor. And I've been doing that for about 13 years now. And then I just joined Saildrone this year and have started working with Saildrone Surveyor. And it's just been a really exciting, technology advancement to be able to do both of the things that I really love the most, which are sailing and mapping, all on the same platform. So that's what we're going to talk about today. So I'm not going to talk about why it's important to map the gaps, because we all know that. We're all a bunch of mapping nerds here. It's all good. What I want to point out, though, is that a lot of those gaps are in the high seas, and that can be very difficult to reach. It can be difficult to get funding to map areas outside of one's country's territory. It can be very time-consuming to get, across the far reaches of the ocean to some of these far corners. And that's where a platform like Saildrone Surveyor can really help, solve that problem, because it's a very cost-effective and environmentally friendly platform with a much longer endurance than you might find on a traditional research vessel. So a Saildrone is an uncrewed vehicle, and this type of platform is very customizable for a lot of different sensors for different types of missions, and they sail all over the world using wind propulsion and solar power. We have 3 different platforms. We have the Explorers, the Voyagers, and Surveyor. So the Explorers have been around for about 10 years now, and they are essentially customized for the mission. So from a bathymetry perspective, they may have one sonar on board, a single beam, an ADCP, or a wideband mini to look at the water column. Voyagers will focus on shallow water coastal mapping, and the Surveyor is our deep water workhorse. So this vehicle has a lot of the systems that you would find on a traditional oceanographic research vessel. So all of the Saildrones have standard navigation equipment for safe navigation around the globe. There is also a pilot that is watching these vehicles at all times. So we have a fleet of dozens of drones that are deployed at any given time. And they also have various other instrumentation, meteorological sensors, seawater sensors, cameras for situational awareness. And then, of course, Saildrone Surveyor has a variety of deep sea sonar systems. So where the Explorer drones are sort of customized for a mission, Surveyor has a specific set of sensors, and the mission will simply decide which ones to use, for a given mission. So these are installed in a gondola, which is below the keel of the vehicle, and have a variety of systems on board to run all of the sonars. So earlier this year, the multi-beams were commissioned with help from the Multi-Beam Advisory Committee and Kongsberg. The 2040 was commissioned in San Francisco Bay, and the 304 just offshore of California, off of San Francisco. And then I joined in May and have been adding a lot of extra layers to the cake. So taking a working system and adding more data logging and data management and processing regimes and workflows for getting the data organized on board so it's easy to manage once it gets ashore. So shortly after I arrived, we did a little test mission off the coast of California where we mapped a small area that had not yet been mapped as an exercise to test some of our new changes. And we uncovered a feature that was indicated by satellite altimetry, and then also another feature that was not previously indicated. So this was just a really great example to everybody as to why we're doing what we're doing, that whenever you're mapping an area that's not yet been mapped, you're more than likely to find something interesting. So once we completed some more of our testing, we began our inaugural expedition, which was to cross the Pacific Ocean from California to Hawaii. And this part of this expedition, this mission, was funded by the Nippon Foundation JEPCO CIBA 2030 project. So this data will be made publicly available. And this was our first opportunity to really sort of test the endurance of the systems on board and navigate and map the seafloor totally remotely. So one of the unique selling points of Surveyor is that we don't have to be in presence of the vehicle. So this vehicle sailed completely by itself, operated totally remotely. I mapped the seafloor from my house right here in Rhode Island. And if you told me 5-10 years ago that I'd be doing that, I would have thought you were nuts. So it was a really exciting mission to be part of and get everything really working well. So along the way, we mapped about 24,000 square kilometers. About 75% of that was new seafloor. So the objective was to cover as much unmapped area as possible along the route. And so these are some images from some of that data that we collected on that transit. So once we got to Oahu, we did a little side survey, if you will, off the coast of Oahu in an area that was indicated for wind planning from BOEM. And this happened to also have Falkor data. So there are not any 304 systems on the West Coast that I'm aware of. So we're not able to make a direct comparison to another platform that has a 304 system. So instead we used the 302 data from the Falkor. So Falkor has a 1x1 302 and Surveyor has a 1x2 304. So we conducted this survey and the differences in the data are very small, a couple of meters, and mostly in the overlapping areas where there's some sound velocity artifacts. Surveyor didn't collect a ton of sound velocity profiles, and neither did Falkor, so they were kind of both even in that respect. And the differences between the two surfaces was on the order of a couple of meters, which is a really small percentage of the water column in depths from about 200 to 1,000 meters. So this was a really great result, just to show that the data collected on this platform is very comparable to the data quality collected by a more traditional research vessel. So of course, using a new technology, this new platform doesn't come without any challenges. Anytime you put any new gizmo out to sea, it's going to have some challenges. And one of the unique challenges that we experience while sailing and mapping is with line planning. So where you are working on a traditional vessel, motor vessel, you would more than likely plan your survey lines parallel to the contours so that you have a nice even swath on each side of the vessel. But that's not how we work here, because we are trying to keep the vessel under sail as much as possible to maximize the endurance. So Surveyor is unique because it does also have an engine, and that's mostly to supplement charging for the batteries to run all of the systems. The deep water systems are just a huge power draw. So we do have the ability to use the motor for propulsion, but we try to maximize our endurance by sailing as much as possible. So in order to do that, though, we have to plan our lines to utilize the optimal sailing angle to the wind, and that's not always terrifically ideal compared to the topography. So on the left, you can see the wind forecast with the chart, and, trying to figure out the line spacing and filling in the area. And then once we get a little bit closer, we get the more recent forecast, then we can, adjust the line heading as needed. And then on the top right, you see that now that our lines are going up and down the slope, which is less ideal, we just have to account for some time to fill in the gaps that we know we'll have once we're going up the slope and our swath is narrowing. So we do our main lines under sail, and then we come around and we do some short lines to fill in the gaps. So the bottom left is our sort of final route. The bottom middle is our progress, just a snapshot of progress. You can see there where there's some gaps as we go up the slope, and then we go back and fill it in and have our nice clean surface. So once we finished in Oahu, we made our way back to California. So all told, we mapped just under 50,000 square kilometers on our first round trip mission. So then what do we do with the data? So this is the interesting thing, because we are a commercial business, so we can't just hand out our data to everybody. I would love to do that. That would be great. I'm a big fan of sharing data, but we have to, make money to stay alive. So instead of being able to share the data, what I am able to do is share the metadata. So on Arc Online, I have two layers. One are multi-beam track lines, and the other one are multi-beam coverage polygons, as shown here. And what I intend to do is share the track lines and the polygons of all of our multi-beam data, regardless of funding, so that everybody can see where we have collected data in the world. So that way it can be integrated, into your own tools like our Crow or other web map services that you may have, but more specifically into the IHO DCDB in the industry layer. So the goal here is that when you go to the DCDB to look for existing data, although we can't share the grid itself or the raw data necessarily, depending on the project, you'll at least be able to turn on this layer, look in that region, and see that we do indeed have data. If that data is available, like the Hawaii Transit will be made available because that was publicly funded, then that will appear in the DCDB, the grid will appear. But if it was not, if it was privately funded or internally funded, then it will show up as a track line or a polygon, and you'll be able to get connected to our website for more information to request access to that data. So that is where we've been this past year, and I'd be delighted to take some questions.
Thank you, Colleen. We have two questions. From one, is there any problem you face with air bubbles?
Not so far. That's a problem that I've experienced on several other ships, and it really just depends on the design. But having this gondola structure, as I experienced on other research vessels that I've worked on, really helps remove that problem pretty significantly. So I've only really experienced having that issue on other ships when we're like in really, really heavy weather. But we haven't been in much greater than about 25, 30 knots wind so far. So we haven't had very high sea conditions, and usually we're going to be having the wind on our beam rather than on the nose. So we haven't experienced that yet, and I don't really expect to.
Okay. One more question. Could you say something about the cost of data per square kilometer or per line kilometer, and compare shallow water to deep water data sets?
Yeah, we're still sort of working through, how best to price that, because the area that we're able to cover really does depend on the depth, right? So the amount of overlap that you need and the data density for that particular system. So I don't have any numbers specifically to give you, but you can absolutely send us an email and we can get that information to you.
Okay. Our last question, and any plans to send out multiple surveyor drones like you do with the smaller platform?
Yeah, absolutely. And so Surveyor is the first one of several, and the Voyagers will also have several. So the goal is indeed to have multiple drones working on a single survey project moving forward, so that we can have lots of data coming in all at the same time and really attack, a whole region as one large project.
Okay, and sorry for last one question. Can you release your data for free, say for every n kilometer spot sounding?
So the data release really depends on our funding source. If we do a project for NOAA, for example, the data will be made publicly available. The Nippon Foundation funding specifically stated to make the data available. So it just sort of depends on the mission goals and what the funding agency wants to see us do with the data. So in some cases where it's going to be, a project will be funded by a private company, such as a wind farm company, for example, they would not want it to be made public. And I don't think that I would be able to release anything other than the metadata.
Thank you very much. There are some questions at remains. So could you type in the at the Q&A section later,
Absolutely.
please?
Thank you so much.
The second speaker is Mr. Ken Childress. He is Chief Revenue Officer of Terradepth. Terradepth is developing a concept of operations based on a unique marine vehicle to efficiently survey the ocean, its contents, and seafloor. Can please present further detail of Terradepth's technologies? Floor is yours.
Okay, I hope everybody can see the presentation now and hear me okay. I trust it's working fine. So thank you, Toshi, and Colleen, thank you for the presentation. Always good to hear what's going on at Saildrone. My background, as many of you know, is also in developing surface sailing vessels in the past, but taking a turn here over the past several years and working with Terradepth now and developing autonomous underwater vehicle systems that we're scaling for high resolution ocean data collection. So a bit of a different platform than the Saildrone, which is, a massive collector. Ours is a more focused collector, but we are also working on the ability to keep those vessels out for extended periods of time so that we can run longer missions, collect more data, get more information, and hopefully make it more affordable to do same. We're also all about improving the user experience with that data. So it's kind of a two-step process. Gather the data, then manage the data and make it more immersively useful for the user. So from the standpoint of scaling the systems, our concept of operations, which we are working on right now, involves the use of vessels in pairs, and the vessels would operate together. Typically, one vessel will be on the surface. It's the vessel that is providing communications and navigation solutions to the vessel below, which is providing survey operations while the two vessels operate. The unique thing about the pair is that each vessel is able to recharge itself when it comes to the surface, and therefore the vessels are able to stay out as a pair for extended periods of time. We're currently working toward about a 14-day deployment time, and we hope to extend that in the future as the vessels roll out. So the idea here is hopefully to, over time, reduce or eliminate the need for manned surface vessels in a lot of different survey missions and opportunities, excuse my voice, and to, again, reduce the cost of gathering that data and to extend those mission durations from days at a time to weeks at a time, concept being similar to what's being done with a lot of surface vessels. But we believe this is really, a unique attempt to do this with subsurface vessels so that we can get really large quantities of very high resolution data in both focused and broad areas. So operationally, we have the first vessel that we've completed. We did this with a partnership with Cellular Robotics. They're up in Vancouver, BC. We had the vessel built in a bespoke fashion after the design of what they refer to as their Solus LR vessels. And these vessels have been operating now for a couple of years. So this vessel has actually been completely tested both at sea, as well as we've done a lot of testing here in Austin. Since we're not next to the ocean, we're next to a pretty large lake called Lake Travis. And we do a lot of our operational and subsurface operational testing there and payload testing. So we've basically completed that first round. We've now taken the vessel out of the water and it's in the shop. And our focus right now is working on what we call the automatic recharge system or autonomous recharge system that goes into the vessel. So as you can see, the vessel is a significantly sized vessel. This vessel is 9 meters long. The section that you see in the center there with the pressure vessel included in it is actually the Terradepth engineered portion of the vessel. The four orange and aft blue sections basically were the size of the vessel as it was delivered to us from Cellular and initially tested. So the state of the vessel right now is it's going back, being put back together. It's actually further along than this right now. And about the middle of December, we will put it back in the water and begin the recharge testing cycles for the vehicle. So that testing will go on for a few months. We're going to be moving it out to the Gulf of Mexico, doing some longer range testing with regard to recharge and operations, and then beginning to do some integration of additional sonar packages and other kit that we're looking to put on the vessel. So just, a lot of people are curious about the power system. The power system is actually developed by a company up in Minnesota called Cobra, who specializes in developing high-powered, high-output engine systems for unmanned aerial vehicles. So we met these guys and said, hey, this looks really interesting. This was a couple of years ago. The little picture in the lower right-hand corner is a picture of the engine. It's about as big as a loaf of bread, and it has extremely high output. It'll generate between 6 and 9 kilowatts of output power. So we can recharge, for example, a 40-watt battery string in under 10 hours. So the cycle time on the vehicle's going to be about 8 to 10 hours of recharge time on the surface and anywhere from 12 to 20 of underwater operational time, depending on what we're running underwater. So it's a unique process, and we're really developing some new application for pretty cutting edge technology to be applied here. The carbon footprint of this thing's about the same as a Vespa, so it's very, very extremely low. And interestingly enough, the engines are primarily manufactured using an additive manufacturing, or if you will, 3D printing type of a process. So just applying a lot of new things here to get the size, weight, and output of the engines at the right place. So the final piece of this is we're developing an onboard data processing system. Currently, we're able to collect and process JSF files using an EdgeTech system, so we can get multi-frequency, high-resolution side scan data. We're also running that through an adapted processing system that allows us to drape bathymetry over the side scan so that we get a 3D point cloud representation. And then we can use that point cloud to run through a machine learning algorithms that we're working on that allow us to identify objects of interest or comparative objects, and then we can flag those objects for further examination. So by the time the data is processed through the onboard data collection system, we have a what I would call a post-process file that's actually usable, but hasn't been fully corrected. So the data then, or those files then, can be uploaded to our portal, which is a viewing portal that is a Google Earth type of a portal. You can see a picture of it there. I'm going to go into that a little more in depth here in a moment. And we refer to it as Absolute Ocean. So once the files are loaded into that file, then they're immediately available for viewing and then for analyzing, and they can be shared and they can be additionally processed and then turned into a final deliverable. So a little bit about the portal. This is what you're presented with when you get onto the portal. You can see it is a Google Earth type of representation. We actually use a software platform developed by a company called Symposium. Some of you may be familiar with that. It's geospatial, high-end geospatial platform driven by Bing as far as mapping is concerned. So, you know, the geospatial accuracy of the maps and the ability to be able to, you know, do corrections and run through those types of things is all available within the mapping system itself. So it's a cloud-based file management system. All of the files go into a cloud system that we manage, and then they're pushed to the geospatial platform. Viewing of the files is via any browser on any system. So effectively, operationally, you go in, you can see the dots, you get in close enough to the area that you want to. You can then do a couple of different things. You can surround an area and open up a bunch of files at one time. You can open up multiple files, or you can open up one file. So you really pretty much have control of what you're able to view. And so you just click on them and open the files. There's no third-party client software that's involved at this point. And the files can be annotated, they can be shared. You can click an area, for example, and then send it to somebody else who wants to or needs to look at the file, and they can look at your annotations, and, you know, those types of things can be done. And then determinations can be made as to whether or not files need to be additionally processed. The raw data files behind the viewable files can then be downloaded, again, reprocessed and uploaded back to the system. So it's a fully interactive type of a system. So the thing is, we didn't want to just make it a system that we could load our data into. So naturally, it's a system that we effectively can load anybody's processed data into, and we also can load your unprocessed or pre-processed data files so that they can be accessible to, you know, anybody that you want to share those with. So data that's loaded into the portal can become immediately shareable to anybody from a, you know, public standpoint, and you can import your data. And we've imported quite a lot of publicly available data. There's a number of tools that are being made available on it. So you can do measuring, you can do area measurement, you can do underwater surface profiling. You can, gather compare data files from one time to another file. And all of the data is displayed at the available post-processed resolution that it's sent into the system of. And then we also do other things like, from a mosaicing standpoint, we're able to fuse data files together so that we can create mosaics that are consistent with regard to the representation, read depth, and other things like that. We currently have 2,200 files or more in our database. And most of these files have come from public sources, although a lot of them are Terradepth collected files that we've done, you know, through our testing. But we've collected files from NOAA, UKHO, EMODnet. A number of commercial clients have contributed files throughout the process here, and the database is growing. Again, the important thing to remember here is this is all accessible via browser with access. So the functionality we look at here, we lovingly refer to it at this point as ping to browser. The idea here is you can collect your data. It can be curated into a group if you want, so that only people who you want to allow to view and work with your data can be allowed. It's accomplished basically via username and logon type of an application, or as I said, your data can be made shared, publicly available across the audience. We have support for different types of data sets that are post-processed into a number of different file formats. We can do side scan data. We have multi-beam data. As you've seen, this is a representation of a JSF file that we did here not too long ago. We've also incorporated SAS data from, for example, Kraken, as well as some LiDAR data and satellite bathymetry data. So the type of data doesn't really matter in terms of what it was generated with, as long as we can manipulate that file and then put it into the geospatial reserve and make it available. Again, as I mentioned, user group access to private and public data sets can be set up within the system, and then you get username and password protection. Interesting, just these particular files here, these were some test files that we ran recently, and these files were shot with the EdgeTech 2205 system that was running on a Teledyne Gavia. And this file, as you can see, is 0.36 in the metadata on the left, 0.36 square kilometers. It was shot in Lake Travis. And from the launch of the Gavia through the mission, the gathering of the data, the onboard processing, the uploading into the portal, and making it viewable in this format right here took about 1 hour and 15 minutes. So at that point, then we have high resolution viewable files that can be worked on and shared. So as I mentioned earlier, you can view single files, or you can do it in regional mosaics. This is an example of a regional collection. There are 5 files that are open right here. Each one's designated by its, particular drop dot there. And we've put those files up and then fused them together bathymetrically as best we could at this point to, get rid of any seams. There's still some, stuff going on out here. So not all files smooth out as well as others do, and that's a process we're still working on, but it's getting better all the time. So the nice thing about this is once you open this file like this, then you have the metadata pop-up window over there. This is an example of the types of metadata that you can get. There's also other data, depending on what's available in the file, that can be displayed here. You get a depth map that gives you your depths correlating to the, the colors in the map file. And then it is an interactive pan, tilt, and zoom viewing. So you can zoom in to these files all the way down to their finite resolution. You can turn them, tip them, get in, take a get a more of a 3-dimensional look at the surface, and really have a good look at what's going on in the file. And then, as I mentioned earlier, if there are objects of interest in there, you can then annotate those things. You can share them with the other people within your group. Say, hey, take a look at this, send them a link. They can then click the link, open the file, look at what you were looking at. And then as additional processing is determined that needs to be made, we can make the raw data files available through the system for downloading and sharing also. So the whole idea of the system here is to provide something that is immediately accessible. We are not anywhere near trying to replace processing systems like Camera or CARIS. The processing is still done on those systems, and we actually work with some of those vendors to do our processing. And but the output part of this, once the files are processed into formats such as LAS, GeoTIFF, we can deal with JSF files, any type of XYZ 3D, bathymetry draped file we can work with. And then, of course, side scan files or side scan point cloud files. So, a wide range of files, once they've been processed and become viewable, then we can make them available to whoever you want to. It's a pretty immersive experience for those of you who have dealt with the outputs of systems such as Fledermaus. You get kind of a similar experience with this. I guess some people have termed this as kind of a Fledermaus light. Again, we're not necessarily trying to compete with those things. We're just trying to make data more immediately viewable, and we can handle excessively large data sets. The back end of this in the cloud is built to deal with petabyte scale file movement and formatting. Currently, it's based on the GCP cloud. We've done most of our own back-end engineering here using, advanced engineering techniques and security systems like Kubernetes. So it's a real live, high-end, back-end, high volume data system. So I think that's it. That's a look at what we're doing both from our vehicle development standpoint as well as what we're doing with the Absolute Ocean data portal. Absolute Ocean as a data portal will be available for customer use as well as public use here first quarter of next year. We will be launching it at the Oceanology Conference in London. And so there's still a lot of good things that are going to go into the system. And, you know, we are happy to show it to you, happy to give you a demonstration of it and show you what you might be able to do with your data files and with other publicly available data. So with that, I appreciate your time.
Thank you, Ken. There are no questions so far. So let's move on. Next speaker. The speakers are Miss Karen Cove and Mr. Andrew Talbot. Karen is Senior Manager of Products Teledyne CARIS. She has experienced marine geospatial and fisheries and a keen interest in mapping to support the safe and sustainable use of the ocean and coastal environments. Andrew is a bathymetry advisor of United Kingdom Hydrographic Office. He gets involved with handling of bathymetric data as well as providing training and advice with a view to understanding and improving data quality. Karen, Andrew, this session is for both of you.
All right, great. Thank you, Toshi. I'll start us off, and hello to our global audience. I hope you can see my full screen there. My name is Karen Cove, and like Toshi mentioned, I work with Teledyne CARIS. And we're here to speak with you today about some AI-based tools that we've made available to the ocean mapping community to enable achieving the Seabed 2030 challenge and hopefully many other things as well. We know there's many wonderful organizations now donating data and many data collection exercises underway right now to map the seabed at scale, like we just heard from Colleen and from Ken. But to fully meet the challenge, we also need to scale the processing of that data along with the collection. We need to do this at a scale that's not in practice in the ocean mapping industry today. And UKHO and CARIS, we really believe that the processing underpinned with the right toolbox of technology, techniques, and approaches, including AI, that this can be done, and we're working together to try to make this a reality. So Andy and I are pleased to be back here at Map the Gaps. We presented on the same topic, I think it was back in January of this year, but there's been really significant progress made since then, and we wanted to share that with you, including an announcement of a memorandum of understanding with Seabed 2030. And I'll start off just presenting a bit of a high-level view of what we're trying to accomplish, and then Andy's going to get into the more technical aspects of how the tools work. So in these early days of understanding the potential to leverage the cloud, like Ken was just talking about, and AI alongside other technology to the benefit of our community, the ocean mapping community, you know, there has been a lot of research and experimentation and evaluation by universities, by government, and in private industry. And, you know, I'd even say there's been really an explosion of interest in leveraging AI in the wider marine domain over the last few years. You know, when you read articles online, it's everything from identifying individual fish faces to tracking the movement of right whales to detecting kelp beds and seagrass, and some of the things that we've been doing, like cleaning noise out of sense data and identifying features of interest in point clouds and images and everything in between. So much of this is still at that exploratory research phase, but you know, it's advancing quickly. And you know, we're both kind of early innovators in this space, and we decided about a year ago to work together to develop AI capabilities for the benefit of hydrography and the blue economy, with tools that are fit for purpose for the workflows and products in this domain. And this teaming is based on our respective resources and areas of expertise, and is meant to strengthen the tools that we create together and to accelerate the adoption of AI across our community to support the successful mapping of the seabed and ultimately, hopefully, many other activities as well. So with this focus of moving past that research phase and really bringing commercial products forward that a large number of people in our sector would be able to use, we decided to first focus on tools that identify and automatically cleanse noise from sensor data, as that's what brings the most benefit to the most users. I admit this does not win the prize for the most glamorous topic, but it does address the most time-consuming, boring, and manual aspect of data processing. And let's unpack a little bit more why we focused on noise. I think everybody in this audience knows that, you know, any survey is going to suffer from the presence of noise, whether that's, you know, a commission survey for safety of navigation, or, you know, simply the collection of transit data. Some degree of processing, quality assurance, and validation is going to be needed to enable that data to be used with confidence. The criteria around how good the data needs to be in terms of that processing and quality is going to differ depending on the end use, but inevitably cleaning noise out of the data is part of it, and it's time consuming and manual. There are some semi-automated tools and processes available which can reduce that time, but these usually work on some sort of statistics, and they can work well in some cases and not in others. It's difficult to find sort of a universal approach with them, and sometimes they can cause more harm than good in your efforts. So machine learning is actually really great at pattern recognition and prediction. So it's a wonderful fit for a job like this, you know, of identifying noise in 3D point clouds. You know, the training of the model is intensive and requires heavy duty hardware and access to many data sets with the characteristics you want. But the actual use of the model is really, really simple. It can just be hosted up on the cloud. And as you're working away in your toolkit, you can just call on that service and push your data up and have the results pushed back down to you. So it's very seamless. So the UKHO and CARIS collaboration has come about over this last year, but that's after both organizations had already been spending some time investing in their own, you know, AI programs. The UKHO has been investing in the use of AI as a way to use new approaches to deal with the increasing levels of bathymetric data cleaning and verification tasks to support their SOLAS program and other mandates. And they really see those tools as the enabler that's going to let them handle more data. It's not about replacing people, it's about handling more data and ultimately get more data on products more quickly to support SOLAS and that broader marine data mandate. And they have a data science team at the UK Hydrographic Office that has developed, you know, various AI models, including the one that we're going to look at today with Andy Talbot. And on the Teledyne CARIS side, we've also been investing really heavily in R&D for both sonar and LiDAR applications, with a focus on, you know, noise detection, which is the one we're going to focus on today, land-water interface as well. We have a bathymetric LiDAR system called the Supernova Sysmil, which Charles de Jongh is going to mention. And we've been making use of AI to solve problems that, you know, are difficult kinds of problems to solve. We make these tools available commercially through our CARIS HIPs and SIPs and other software packages. And like I said, you know, the idea is that the tools are really easy to access right in that workflow that you're already using. So in June of 2021, I'm pleased to say the UKHO and CARIS established an MOU with GEBCO Seabed 2030 for the regional data centers to make use of some of these tools. you know, to build up a better understanding of how they can help reduce that effort that those teams are putting in to deal with all this data that's being donated and collected, and bring that into their program and ultimately their map. All right, I'll just pop this little slide up to give you an idea of some of the other commercial tools that sit alongside the sonar noise classification tools. And these are all ones that people are using as commercial products today. All right, I'll pass things over to you, Andy.
Yeah, thanks a lot, Karen. Yeah, so I'm just going to talk a little bit more about the sort of development of these tools. So at the UKHO, we started looking at this sort of early 2019. Our data science guys looked at a lot of different sort of AI techniques, machine learning, deep learning, statistical ones, and things. We put you know, small bits of data through each little tool that had started developing, just to kind of see which ones were worth taking further, basically. And we identified two of those that seemed to sort of be showing promise. One of them was using a technique called deep learning, and the other one was a bit more statistical technique, which is called a generalized additive model. So these are kind of known models. You can get the tools off the shelf kind of thing, if you like, and then adapt them to your own kind of purposes, which is what we then start to do to tailor these to sort of specific data types. So next slide, please, Karen. So at the same time we were looking at AI, as Karen said, the CARIS team were also looking at the same sort of tools, and they developed a tool called the sonar noise classifier, and this actually uses the technique of deep learning, which is one of the ones that we kind of settled on as well. And like us, they found that this basically works well with contiguous surveys, you know, high accuracy kind of IHO order commissioned kind of data sets and things, and that's kind of what that's sort of tailored towards. Their service, like ours, runs in the cloud. As I'll sort of mention a bit later on, you know, these methods do need a lot of grunt work to kind of work effectively. So this is embedded in their kind of cloud services that they offer, the Mira tools. And if we just have the next slide, please, Karen. So the other method that we looked at was the GAM, the generalized additive model. Now, we started focusing more on this because we found that actually this was very good at cleaning single tracks lines of multi-beam data. So these are sort of transit lines that sort of scientific vessels gather quite a lot of the time. And this was a technique that seemed to produce much better results than the deep learning. This method from the UKHO tools is the sort of most advanced so far, and it's basically operationally kind of ready to use, whereas we're still doing work at the UKHO on the deep learning tools that we're developing, so they will come along sort of later on, sort of thing, from our side. So the GAM, as I say, effectively kind of fits a surface through your data, and then basically rejects data that is a specified distance away from that that surface. And once we found that it kind of worked better on these kind of single track lines of data than deep learning, we kind of started developing it more with that in mind. So effectively, you've got data sets here with less redundancy. They span huge distances, areas of the globe. They might span, you know, more than 1,000 kilometers from beginning to ends. They're big geographical ranges and big depth ranges as well. You know, perhaps starting sort of 10 meters of water, going down to sort of many thousands. So we started developing our tool that could scale very well in this way, and adapt to these data sets and clean them as sort of efficiently as possible, and as hands off as possible. This is kind of what we wanted to develop, and to develop a tool that would not over clean. So it would take the noise out, but to a point where it's still leaving all the good stuff in. So if we have the next slide, please, Karen, I'll just show you some examples of GAM kind of working. Just a few pretty pictures here, basically. So the picture there at the top is your noisy data that's been pushed through the GAM tool, and the grey points there are what's been identified as the noise, and then we reject those, and then you're left with the data set there at the bottom. So this is a single track of multi-beam data in very deep water. As you can see, it's left a few little bits of noise there just below the surface, but it critically hasn't rejected any of the good stuff. So have the next slide, please, Karen. I've got a few more just examples of this tool working. So again, top picture there is the unclean data set, which you can see, you know, isn't really bad in the first instance. There's only a little bit of noise in there, but when we run that through the GAM tool identifies that little bit of noise, takes that out, but it doesn't get rid of any of the other good stuff that's there. So it's keeping all of that, which is the sort of the crucial thing we're after. We didn't want it to kind of overdo things that then manually you've got to go back in and fix all those mistakes it's kind of made, sort of thing. So yeah, next slide, please, Karen. Just a few more examples of it working as well, taking the noise out and leaving all the good stuff in. And, you know, it's not necessarily getting all of the noise all of the time, but that's kind of the way we would like this to work. We'd rather the user has a little bit of work tidying up to do at the end, potentially if they need that for the, depending on the purposes, at the end use of the data, rather than actually, like I say, overdoing it and actually having to then go and repair holes in the data and things like that. Okay, so next slide, please, Karen. Couple more examples here. Are we doing well? The one on the left, yes, it's done better. The one on the right, not so well. So just coming clean here, that, you know, it's not necessarily going to work perfectly all the time, but as you can see there, it's got rid of a lot of the noise, left a little bit in, maybe a little bit too much. But the stuff that's underneath the data set there is probably less critical anyway. But, you know, there's a little bit of tidying up perhaps required by the user, but it's very minimal. And depending on your purposes and your uses of the data, that may well be enough, basically. So we've developed this tool to be sort of hands-off, as automated as much as possible. So there's not really any settings on it at all. You just throw your data at it and you get your result back. You know, and for our purposes, the way we're thinking about this, if it can just do 80 to even 90% of the work that, you know, would normally be done by humans, that's great, because that saves a huge amount of effort. And okay, the user then has to just finish off the last little bit. What we don't want it to do is 120% of the work and overdo it, so then you've got to backtrack and undo what it's done. Okay, that's kind of our kind of thinking when we were kind of sort of trying to tune this and develop it. So next slide, please, Karen. Just a few technical details about how these kind of work. So we've done all our development in Python, and we've got these tools running on Linux boxes, and we use GSF files, generic sensor format files, for our input and our output to these tools, just because that you know, means they can be used with a variety of different types of software. That's kind of an open source format that most software can export and import. And we have managed to run these locally. We've even managed to clean some data on a laptop offline, but very small data sets, because these tools just need a lot of grunt to work effectively. So yeah, you can do more if you've got a server grade machine or workstation, of course, but you still, you know, it's not enough. So we have ours in the cloud, very much like the CARIS tools, and we have a scalable cluster of like 100 machines in the cloud that kind of scale up if it needs that performance, and it scales them back when it doesn't. So you know, typically here as an example, you know, we can clean, you know, up to sort of 450 gigabytes of GSF files, which is quite a lot. If you scale that up to a sort of equivalent CARIS project, you're talking between 4 and 5 terabytes of a CARIS project, which is pretty big. And we can do that in sort of 10 hours or so, and that's all just number crunching in the cloud, so the human being can go off and do something else. So we're continuing to work on our deep learning tools, as well as our you know, this GAM tool that we wanted to take further. And if we go to the next slide, please, Karen. So these are just also some metrics, basically, because obviously what's really important here is there's no point in doing any of this if you're not really kind of getting some benefit out of it and saving some time, which is really our reason for kind of doing this. So we've done a couple of examples where we have cleaned a data set manually, kind of the old-fashioned way, just using the tools that we had available before, and then we've done exactly the same data set from scratch, and we've run it through the GAM tool and done whatever manual tidying up we needed to do afterwards. And we're finding even now that we're better than 50% of the time. You know, we're under that, so that's great. I mean, that effectively means right now we could handle twice as much data effectively. We're hoping to improve on that, because this is when the tools were relying on the GSF input and output for us to do. So that was a bit of a manual process to export and import those GSF files again. Whereas what we really wanted is to have these tools available in our software that we use, which is CARIS HIPS and SIPs. So in our collaboration that we've developed with CARIS over this year, we've basically between us managed to get access to the Admiralty GAM cleaning tool available in CARIS HIPS. It was built in to the software this summer, and we officially launched it in October this year. So we can have the next slide, please, Karen. So this is really good. So now, you know, the COTS software that we use on our main machines has now got a button in there in the menus for the Admiralty GAM service. So any data set we've got in CARIS HIPS and SIPs, we can actually clean using this service, and it'll use our tool to do the cleaning. This is available obviously to other users as well. And what's actually happening now, it saves a lot of effort for us as well. We're not having to manually convert the data to GSF and then run it through our tool in the cloud and then re-import those once we get an answer. All that happens behind the scenes. The user just hits the button to clean the data, and it happens. Behind the scenes, the data gets converted to GSF, gets fired up to the tool in the cloud, and then the answer comes back as GSF. And then what CARIS does is it looks at those flag changes, and it just basically maps those back across to the CARIS project. So it doesn't even do the importing. You know, it skips that step just by mapping the flags back to the HIPS data structure. So effectively means you haven't really changed your data other than those flags that need to be changed to rejected. Because of the cleaning that's been done by the GAM. So you haven't lost any of the flags and anything else that you've done by going to GSF and back again, because you do lose some things in GSF because that can only hold so much information. So this is a great outcome. This is kind of the latest bit of news, I guess, really, you know, since we spoke to you last in January. That, you know, this development of this tool has gone on a little bit as well, but the fact that it's now available in the software is great. It makes it so much easier to use, really. So with that, I'll hand back to Karen just to wrap things up.
Thanks, Andy. And along with embedding the tools in the HIPS software and releasing those commercially, so other people can make use of them as well. I wanted to also mention, you know, we had established this MOU with Seabed 2030, and the goal of that was to give the data centers access to these noise cleaning tools to evaluate. You know, we want to better understand, you know, how significantly they can add value to the data processing pipeline, and how it can help reach those, you know, Seabed 2030 goals, let them scale up as more and more data is collected and donated. The feedback we're looking to get is, you know, going to be qualitative in terms of how good of a job did it do, whether the results are fit for purpose for this community, and quantitative in terms of, you know, the amount of time saved, and we've got our first evaluation going on right now. So we're looking forward to, hopefully next time we speak to this audience, that can be the theme of the presentation. And, you know, we just want to reiterate that this is really early days. It's just the beginning of leveraging these kinds of techniques in our work. And UKHO and Teledyne do, you know, plan to continue collaborating as we believe there is much more that can be done using AI technology to further ocean mapping and bring value to our larger hydrospatial domain. You know, in that case of safety of navigation purposes, you know, we see AI as definitely adding value by reducing the human effort in the, you know, existing workflows that are accepted today by, you know, hydrographic offices and others. But, you know, we'd really like to speculate that a scenario that is much more reliant on these kinds of tools and could be feasible for navigation applications like Seabed 2030. And so we'd really like to keep streamlining this workflow, bringing in this kind of technology where it's a good fit, and see if we can achieve something that is very, very automated, and really it's just that human over the loop scenario, you know, when it's not safety of navigation at stake. So we're really excited to keep working on this. We're looking forward to that Seabed 2030 feedback and identifying other areas with that group where we can bring value to the program. We're looking also, you know, for other partners to work with that are involved in maybe other trusted crowdsourced bathymetry initiatives, you know, that are having to have these highly automated pipelines for processing data en masse. Be very interesting to see if these tools can be leveraged by any other groups to meet their goals. And, you know, the research programs continue. At CARIS, we've really been focusing a lot lately on identifying classifying features in point clouds. And at the UKHO in the data science team, folks are looking at a lot of interesting things, you know, interpreting satellite and drone imagery for mapping mangrove forests, detecting kelp beds and seagrass, using satellite-derived coastline, automated offshore infrastructure detection and identification from SAR imagery, and looking at AIS data analysis to better understand locations, vessel activity, volumes of traffic, and even doing analysis, you know, to understand water clarity so they can determine the best times to perform surveys around the world. So a lot of things going on, just food for thought. And if you have ideas, you know, I welcome you to reach out to Andy or I. And if you want to know more about the tools or talk about any of this, you're welcome to. And I thank you very much for your attention. Thanks, Toshi.
Thank you. Thank you very much, Karen and Andrew. We have 3 questions at question and answer and chatting. So I select the one question from the chat regarding sonar noise classifier and the GIM. How is their result with tight and narrow seafloor feature and watercolumn data? Please reply very shortly.
Ooh, yeah. Sorry, can you hear me at all?
Yeah.
Sorry, yeah. Sorry, technical hitch there, I think. Yes, that first question about the sonar noise classifier and GAM and results with the tight and narrow seafloor. So is that right? Is that the first question we're answering? I would say from the results we've seen so far that it behaves pretty well with that. It's never a guaranteed thing, you know. It's always worth checking your data, your results, if you have a, you know, if it's safety critical work that you're doing. But I say the way we've sort of tuned the tool so far, we found that it actually works really well over reasonably complex features. And I say, you know, it may struggle with complex wrecks, for example, because, you know, it then may get a little confused as to what's real and what's not real, especially if you've got fish and nets on the wreck as well. So there'll always be ways that you can fool these tools. But from what we've seen so far, yes, it's pretty good. Not sure about the water column bit, because these tools are only really designed to work on the point cloud data. It's not, we haven't started developing them in any way to kind of examine water column data. Okay, so hopefully that's answered that one.
Thank you, Andrew. And I remain that the question and answer 3 questions. So please reply with text later. Thank you very much, Karen and Andrew. And also thank you for organization's cooperation. Let's move on to the next speaker. The 5th speaker is Mr. Charles de Jongh. Charles de Jongh comes from the Netherlands and has many years of experience in the ocean mapping community. He now manages bathymetric project for the Norwegian company Terratec and focuses on mapping gaps using airborne radar bathymetry. Charles, floor is yours.
Thank you very much, Toshi, for the introduction and for the opportunity to have a presentation at this MtG Symposium. As mentioned, I'm working with airborne lidar bathymetry project at Terratec in Norway. Terratec is the biggest geospatial survey company in Scandinavia and has always been at the forefront of technical development. We have many years of experience with airborne lidar surveys, including bathymetric lidar, which is what I would like to talk about today. I will talk about what airborne lidar bathymetry is, what the advantages and limitations are, the equipment we use, and the products that can be created. I will discuss how this effective technique can help mapping gaps, and will conclude with an interesting use case of a survey we did in Norway. What is airborne lidar bathymetry? Well, to summarize, basically a strong green laser pulse is shot downwards from a lidar sensor in an airplane flying over water. Green light is normally used as this frequency can best penetrate the water. The light hits the water surface, penetrates the water column, and reflects from the bottom, back to the sensor in the airplane. The sensor digitizes the incoming light photons and measures the difference between the water surface and the water bottom. Note that measuring with light is about 150,000 times faster than measuring with sound, which is traditionally mostly used for measuring of water depth. The time it takes for one laser pulse to return to the sensor is about 0.3 milliseconds, so less than 1,000th of a second, and the airplane moves about maybe 2 millimeters in that time frame. So as we're measuring the difference between water surface and bottom with light speeds, the technology needs to be very precise. Pulses, laser pulses, are normally sent out tens of thousands of times per second, and the result, when combined with precise positioning, is a geospatial point cloud with high density and accurate bathymetric depth measurements. For those that are familiar with it, with our advanced sensor, we can reach UKHO special order accuracy. With airborne lidar bathymetry, you fly over an area with around 200 to 250 kilometers per hour. So you can survey much faster than with a multi-beam echo sounder, specifically in very shallow areas where a multi-beam cannot reach or only has a very limited swath width, as can also be seen on this picture. Another advantage is that with a topo bathymetric lidar sensor, you can, next to mapping underwater elevations, also simultaneously map the elevations on land with a high point density, giving you a seamless elevation model of the coastal zone, which is difficult to achieve with other survey methods. So I think that specifically for this MtG seminar, it's important to emphasize that airborne lidar bathymetry is a very effective tool to map the coastal zone gaps that often exist. Of course, mapping is not limited to coastal zones. The technique is also very appropriate for the mapping of other water bodies, like rivers and lakes. There are also some limitations to bathymetric lidar that need to be taken into account. To be able to measure the water depth, you are depending on the laser light that is sent out from the sensor to be reflected back into it as well. So you need to at least reach the bottom of the water. Until what depth a sensor is able to get a bottom return is depending on the strength of the laser. the local water transparency, and the local bottom reflection. The best bathymetric LiDAR systems that are available, like the one we have, can reach about 3 times the visible water depth. And in general, transparent, so not turbid water, with a high bottom reflectivity gives deeper returns. On this roadmap, you can see a global overview of water turbidity. Blue values on this picture represent clean water, red values turbid water. In general, zones around the coast are most turbid due to the fact that in these regions, there is most sedimentation in the water. The range of depth you can reach can vary enormously based on the turbidity, from just a couple of meters in very muddy turbid waters to up to around 60 meters with very clear waters and good bottom reflection and a good system. I would like to give you a quick overview of the workflow we use for airborne LiDAR bathymetry at my company Terratec. We have 2 Cessna Grand Caravan aircraft in which we can install our bathymetric LiDAR sensor, the Teledyne Optec Seasmill Supernova, which is basically the best sensor that's currently available on the market. The Supernova sensor is combined with a very good phase 1 RGB camera that takes images that result in a resolution of about 3 centimeters. We always take images during a survey, for example, to create orthophotos, but also to help as a visual aid in the processing of the bathymetric LiDAR data. An advantage that our aircraft have as well is that they have 2 hatches, which means 2 holes in the bottom through which the sensors can look. This makes it possible to combine the Supernova and camera using one hatch with other sensors using the other hatch for a simultaneous survey. We can, for example, use a hyperspectral camera that covers both the visible light, near infrared, as well as the shortwave infrared spectral regions. With these cameras, the spectral signature of features in the water can be measured with high resolution. For example, to find marine vegetation or pollution in the water. So this is the equipment we use for data collection. And after data collection, the sensor data is processed at Terratec. For the initial processing, georeferencing, noise removal, and classification of the Supernova LiDAR raw data, we use CARIS software, which makes use of several deep learning algorithms to aid with the processing. And this is what Karen was already mentioning in the previous presentation. Depending on the client requirements, many different types of products can be created and delivered by Terratec, and some examples are shown here. I've tried to list some use cases for which the data can be used after delivery by Terratec. For example, nautical charting, coastal zone planning, flood mapping and modeling, marine biology, and marine geology. This list is based on actual examples of how airborne bathymetric LiDAR data is being used. And what I think is very interesting with bathymetric LiDAR, specifically in combination with imagery, is that the data that is collected once can be used by many different stakeholders for many different use cases, and as such have an enormous economic and scientific value. A good example of this is the marine base maps for the coastal zone project in Norway, for which we recently executed a survey where we used bathymetric LiDAR in combination with high resolution RGB and hyperspectral imagery to survey an area around Stavanger on the west coast. The Marine Base Maps project is a pilot project executed by the Norwegian Mapping Authority, together with the National Geological Survey, the Institute of Marine Research, as well as local municipalities along the coast. The common goal is to better and also more efficiently map the Norwegian coastal zone. And airborne LiDAR bathymetry is one of the main techniques that is being tested, as it's a fast and accurate surveying technique. If this project is successful, the idea is that larger stretches of the Norwegian coast will be surveyed with airborne LiDAR bathymetry. And to give you some context, after Canada, Norway actually has the longest coastline in the world, with a length of more than 100,000 kilometers, including all the fjords and islands. However, good geospatial data of the coastal zone is actually scarce. It's not an easy area to survey, like I mentioned before. So also in Norway, this is definitely an area where there are mapping gaps. A report commissioned by the Norwegian Mapping Authority actually states that only mapping 10% of the Norwegian coastal zone with high resolution maps will already give about a $500 million return on investment to society. So this mapping seems to be well worth the effort. And I can imagine that this is also true for coastal zones of other countries. We surveyed the area for this project of about 100 square kilometers in 2 days with good weather conditions. And the preparations for it consisted, amongst others, of flight planning and making a good assessment of the local water turbidity based on satellite data and also on local measurements to assess what we could expect and when it would be the best period to survey. The data we got back was frankly quite amazing. We achieved depths of over 30 meters with generally a high point density and full coverage almost everywhere in the survey area. In the picture, you can see both land elevations as well as bathymetric depths of up to 30 meters of part of the area we surveyed. And so this is a truly seamless elevation model of land and sea. Orthophotos were also created based on imagery acquired during the same survey. The picture here shows an orthophoto of the same area draped over a digital elevation model of the land elevations and the sea surface. And what I've done in this picture is to actually remove the sea surface, showing the bathymetric depth measurements in the area. And I think this picture shows very clearly what we're doing here when measuring water depths. It's like pulling the plug from a bathtub and removing the water, revealing what was hidden before. This is the same picture, now also including some depth contours and soundings. So now we're getting closer to what will be published on a nautical chart. And I think it's worth noting that we really did some gap mapping here, as the mapping authorities did not have any data available in the shallow areas that were not reachable with multi-beam sonar. So these gaps are now filled. And the mapping authorities were also very happy with the accuracy of the data that we had when they compared it with multi-beam that they had in the same area. What's interesting as well is that with airborne LiDAR, you do not only map the water bottom, but the whole water column. So objects within the water column, they also reflect LiDAR light. And this makes it possible to also map marine vegetation and other objects in the water. And furthermore, when you combine the LiDAR data with higher resolution RGB as well as hyperspectral imagery, which maps the full spectrum of visible and infrared light, you are able to quantify the amount of vegetation in the water and potentially the type of vegetation based on the unique spectral signature. So the fusion of these sensors provides a treasure trove of information that can be interesting not only for hydrographers and nautical charting, but also for many other economic and scientific purposes. I would like to conclude this presentation with a short summary. As mentioned, with airborne bathymetric LiDAR, large areas can be surveyed accurately and efficiently. The technique is probably most efficient for coastal zone gap mapping, also in combination with other advanced sensors, and the resulting data can be used for many purposes. Terratec has experience with the successful execution of bathymetric LiDAR projects, and we can deliver a full survey solution where we execute survey and the data processing and deliver high quality geospatial products according to UKHO or other client requirements. And we definitely look forward to map more gaps around the world. So if you're interested, feel free to contact me by email or LinkedIn. And for now, I would like to thank you for your attention and hand over to Toshi again. Thank you.
Thank you, Charles. This is move on to the closing. So today, I suppose everyone has learned the technologies from autonomous surface and submersible vehicles, collaboration grows, laser light measurement, and the other methods. I look forward to the further development of today's presentation technologies to further accelerate seabed mapping. Thank you for 5 speakers and participants. Please enjoy the rest of the UKHO Map the Gaps Symposium. Thank you very much. Goodbye.